Hello, my name is Deepak Bharadwaj and I have been teaching physics since 2011. After graduating from 2008, I actually initially resisted the idea of teaching for around 3 years. During those 3 years, I switched many jobs. I worked in electronics, finance, as well as software, but nothing really worked for me. I finally landed in teaching, and as you can see, it worked for me. Over the years, it has been pretty interesting, challenging at times, but mostly satisfying and fulfilling. I was with FITCI South Delhi from 2015 to 2018, so I had the good fortune of interacting with Kalash Gupta and Manupriya, who secured AAR 3 and AAR 220 respectively in JEE Advanced 2018. I say good fortune because frankly both of them were from the beginning very self-disciplined and self-motivated. So I can't really take the credit there. Over the years I found that it's the students who are not necessarily top 100 rank material, not naturally confident and not naturally systematic. The students who fail, struggle, get the inputs from the teachers and then improve. I found that it's those students where a teacher can really make an impact. And there have been many examples over the years of such students. The topic I am going to discuss today is the utility of looking at SHM as the component or projection of circular motion. So what do I mean by that? What I mean by that is if you have a typical SHM, simple harmonic motion, I am showing you here a particle oscillating on a straight line, let's say the x-axis. This is the mean position marked as O. This is the right extreme and the left extreme, plus A and minus A, where A is the amplitude. At any instant, let's say the particle is at a displacement x from the mean position. Then, because this is SHM, we know x must be a sinusoidal function of time t. X must be a sine or cos function of time t. As an example, let's say x is a cos omega t plus phi. We know a is the amplitude, omega is the angular frequency, and phi is the phase constant. I'm going to claim that an SHM like this can also be thought of or can also be represented by the component of a circular motion. Now, what do I mean by that? Let's suppose there is a circular motion. There is a particle moving in a circle. The particle is moving in a circle of radius a. It's moving with a constant angular velocity omega. We also have parallel light falling from the top, so that the particle can make a shadow, let's say on a horizontal line. So you see a horizontal line here. As the light is coming, the particle makes its shadow. I am showing the position of the shadow by this length x. Now you realize that the length of this x is same as the x component of the circular motion. Now you'll see that the x component here varies exactly like the position x in SHM. Now imagine how the shadow moves on this straight line as the particle moves on the circle, let's say from point 1 to point 2. You can imagine when the particle is at point 1, the shadow will be here, that is at the mean position. When particle in the circular motion is at point 2, the shadow will be at the right extreme. From point 2, when the particle comes to point 3, the shadow will once again come back to the mean position. From point 3, when the particle goes to point 4, the shadow will go to the left extreme. And from point 4, when the particle comes back to point 1, the shadow will come back to the mean position. The point here is that as the particle is moving on the circle, the shadow on this straight line, the x-axis, or the projection of the circular motion, or the x component of the circular motion, is doing a to and fro motion, which looks like SHM, and I am going to show you that mathematically also it's exactly identical as the SHM equation. To show that, imagine the position of the particle on the circle at t equal to 0. Let's suppose this is the position of the particle at t equal to 0. It was making an angle phi with the x-axis. Since it's rotating with an angular velocity omega in a time t, it will rotate by an angle omega t, so that the total angle with the x-axis will now be omega t plus phi. This is the total angle here, which I am saying is equal to omega t plus phi. Remember, the radius is a, which means the length of the shadow, the position of the shadow or the x component will obviously be equal to A into cos of this angle. So I can say position of the component is same as x equal to A into cos of the angle, and you see the angle is again omega t plus phi. Which means the equation that we get from the SHM and the equation we get by taking the component or projection of the circular motion is identical. Now, what is the utility of doing this? Because after all, when I show SHM like this already is a visual representation, a graphical representation. Why do I need another visual representation for same SHM? See, you'll realize this, the first advantage obviously is that doing this allows you to visualize phase. In this line, you cannot visualize this phase omega t plus phi. However, on the circular motion, you can easily visualize this phase omega t plus phi. It's simply the angle that the particle has rotated with the x-axis. So as the particle rotates on the circle, the angle it makes with the x-axis changes. So the phase in the oscillation changes. So the first advantage obviously is that you can visualize phase of the SHM using this representation. Now secondly, imagine the particle crossing the point P during SHM while it's moving in SHM. It can cross point P in two ways. It can either be crossing point P and moving towards right, or it can be crossing point P and moving towards left. So it can be crossing P while it is moving towards right. Also, it can cross P while it is moving towards left. But on the straight line, I'll have to show both of those situations by a single point P obviously. However, these two situations will be distinct or different on the circle. You can imagine while the particle is crossing point P and moving towards right, we'll have to take this position on the circle. Let me mark this position as star. See, the reason is that in this case, as the particle is moving on the circle like this, you can imagine the particle is moving towards right. Whereas when the particle crosses point P and it again crosses point P while moving towards left, we'll have to take this position. Let's mark this as double star. So those two same positions, the one will be crossing point P towards right, the other will be crossing point P towards left, which on the straight line at a single point, they are now separated on the circle as star and double star. Star will be the position when it is going towards right, and double star will be the position when it is going towards left. So it allows us to differentiate between these two situations. A particle crossing a particular position, but whether it is going towards right or left, we can easily distinguish on the circular motion. To make this idea more clear, I am showing you here 4 different situations in SHM and their corresponding positions on the circular motion. If you see situation 1 and situation 2, in both cases, the particle is to the right of the mean position. That means the projection of the circular motion must be positive to the right of the mean position. For positive projection, what I can do is, I can draw a vertical line like this. When the particle is here or here, in both of these cases, the projection will be identical and to the right. But which one represents position 1, situation 1? I say definitely that it should be this position of the circle which must represent situation 1. Because in situation 1, the particle is moving towards right. Imagine if the particle is here on the circular motion, at the next instant it moves towards this direction. That means the projection moves to the right. Whereas if the particle is here on the circle, at the next instant the particle moves towards this direction, so that the projection moves to the left. So this must respectively be the locations of situation 1 and situation 2 on the circle. Now think about situation 3 and situation 4. In both cases, the position of the particle is negative. That means the projection of the x-axis, projection of the circular motion must be negative. So the particle can be either here or here. Now which one represents situation 3? In situation 3, the particle is moving towards left. If the particle is here, at the next instant it goes in this direction. That means the projection at the next instant moves towards left, which means this must be situation 3, the position corresponding to situation 3. Similarly, when the particle is here, at the next instant it rotates and goes to the mean position. So the projection goes towards the mean position or moves towards right. That means this must represent situation 4. At this point, let's take a numerical example which uses this concept. Let's suppose we have a particle oscillating on x-axis with mean position being the origin, the amplitude being A, the time period being capital T, let's say. And we are asked to find the minimum time taken by this particle to go from an initial position I, x equal to minus a by 2, to a final position f, x equal to root 3 a by 2. Since we have to calculate the minimum time taken, we will discard the possibility of the particle going from I to the left extreme and then going to the position f. For minimum time, we will consider the possibility where the particle is going from I to f directly, that means moving towards right. Now, where are these positions I and f on the circular motion? The position I can be either here or here, but because we have to take the motion towards right, we have to select this as position I, because only at this position the projection will be moving towards right. Similarly, position f is somewhere here on the circle. If I join these positions I and f with the center, we can actually calculate these angles that these radii make with the y-axis, or we can calculate the angles with the x-axis. Now remember, we are considering the SHM here as the x projection or the horizontal projection of the circular motion. Now think, what should be this angle so that this projection here initially is minus a by 2? What should be this angle so that this projection is minus a by 2? Clearly, this angle must be 30 degrees. Only when this angle is 30 degrees, only in that case, the x projection will be a sine 30 or a by 2 to the left, so negative. Similarly, in the final position, the position is root 3 a by 2. That means this angle finally must be 60 degrees, because when this angle is 60 degrees, the x projection is a sine 60 or a root 3 by 2. That means in going from I to f, the total angle that the particle rotates on the circle is 90 degrees. So how much should be the time taken? We know because the angle rotated is 90 degrees or pi by 2, the time taken will be the angle rotated divided by the angular speed. The angular speed in terms of the time period, I may write as 2 pi by t. If you cancel the common factor pi, you can easily see that the time taken comes out as t by 4 or 1/4 of the total time period.